Welcome back, everybody. This is our video solution to problem 2 from quiz 6. In this problem, we're asked to compute the volume of a region using a triple integral. So this is one of the nicest applications of integrals, is being able to compute the size of the domain of integration. And it's one that, for some reason, people seem to overlook quite often, but it's quite easy to define. So remember, our notation for the size of the domain of integration will just be putting the absolute values around. So this means here the volume of E, since it's a three-dimensional region. If this was 2 dimensions, this would mean the area of E. And the volume is going to simply be the triple integral over E with the constant function 1. Right? So that's always the idea. If you want to calculate the size of the domain of integration, you just integrate the constant function 1. So you essentially think about it as you're chopping up the region into these little dv boxes, right? They're these little tiny boxes, and then the triple integral adds them all back up. Okay, you chop up a region, then you add them back together, you get the size of the original region. So what's really nice in this problem is they've actually told us E explicitly, so I can immediately write this down as an iterated integral. So y can go from -1 to 1, z can go from 0 to 2, and then our x value is actually going to go from y to z plus 4. So this is what we called in class a type YZ region. All right, the integrand is just 1, so I can immediately start writing down my differentials. So I have dx, and then dz, and then dy. All right, so this should be a fairly straightforward calculation. On the inside, I'm integrating 1, so I just get the length of the interval, which will be z plus 4 minus y. So y goes from -1 to 1, z goes from 0 to 2, and then I have z plus 4 minus y, dz, dy. Okay, let's integrate with respect to z. All right, the y is just going to hang out here, and when I integrate, I get z squared over 2 plus 4z minus yz, and we evaluate between 0 and 2. Okay, let's see. At 0, everything's going to go away, so I don't have to worry about that. At 2, let's see what we're going to have left. I'll have 2 squared over 2. That's 4 over 2 is 2. 4 times 2 is 8. And y times 2 is, well, 2y, so minus 2y here. Right, now let's see, this is the same as 10 minus 2y. Okay, let's see what happens. If I integrate this with respect to y, I'm going to get 10y minus y squared. And now y goes from -1 to 1. At 1, we get 10 minus 1. And then we'll subtract what happens at -1, which will be -10 minus 1. So we have 9 minus, looks like -11. 9 plus 11 is 20. So that is the volume of E. All right, so just really handy thing to know, right? You want to find, for example, the length of the interval, A to B, you just integrate it. Okay, well, that doesn't seem like a very interesting thing. Okay, but well, if you want to know the arc length of a curve, okay, you integrate it. Okay, again, constant function 1. Okay, this will be the length of the curve C. What if you want to know the area of some domain D? Right? Whoops, not dv, but dA. Right? You integrate the constant function 1. It'll give you the area of D. And in our case, you want to know the volume of some region, triple integrate it, constant function 1. That'll give you the volume of E. Okay, so this is going to happen over and over and over again, and as we get deeper into the course and we see surface integrals, for example, we'll see this show up even again. All right, take care.